Hello, Mr. Honvid. I'm King Crocoduck, and I'm going to try to help you to understand science.
So, question. Is Einstein's relativity theory accurate? Particularly, is the speed of light truly constant? And does this hurt a young Earth theory? Mitch. As far as his theory being accurate, I don't know. There's people argue both sides of that issue, but...
No, Kent. There's no controversy in academia as to whether or not special relativity is accurate. We know that special relativity works because it predicts results with stupendous accuracy. Two central features of special relativity are time dilation and length contraction, which follow naturally and inevitably from the two postulates of special relativity, that the laws of physics are the same in all inertial reference frames, and that the speed of light is the same in all inertial reference frames. If you start with these two postulates, these two equations will necessarily follow. These equations make testable predictions that have been vindicated time and time again. We know that time dilation and length contraction take place because there are a plethora of examples that demonstrate this. When cosmic rays strike the top of the atmosphere, they produce a shower of highly unstable particles like pions and muons, which respectively decay within nanoseconds and microseconds. According to classical physics, even if they're moving at 99.99% the speed of light, this is not enough time for them to reach the ground since they'll decay into more stable products before they're even 1/10 of the way to the bottom. According to relativity, however, time dilation and length contraction make this process possible. Using these equations, it can easily be shown that from the reference frame of an observer on Earth, time is slowing down for the particle, which allows it to last long enough to hit the ground. From the reference frame of the particle, time isn't slowing down, but the distance that it has to travel is shorter because of length contraction, so it manages to hit the ground before decaying. If this process didn't take place, these particles would not be able to get from the upper atmosphere to the ground because they decay before even coming close. And yet we detect them doing exactly that. Particle accelerators routinely extend the lifespans of subatomic particles by accelerating them to ultra-relativistic velocities. Even our GPS satellites use special relativity. Their motion with respect to the Earth is fast enough to warrant corrections to their calculations, and this wouldn't be the case if special relativity were inaccurate. In fact, not only do these satellites need to use equations from special relativity, but they also need to make corrections with respect to general relativity, since they're higher up in Earth's gravity well than we are. These are just some of many examples of how special relativity explains things that classical physics cannot. That's why there's pretty much a consensus among physicists that special relativity is accurate, because it works.
The speed of light, I think it's been well demonstrated, is not necessarily a constant. If it is a constant today in one medium, such as the atmosphere or in space around us, does that mean it's been constant all through history? Does that mean it's been constant in all mediums?
Okay, stop right there. Nobody says that light is constant in all media. The speed of light in a vacuum is different from the average speed of light through water, glass, and other media, and this has been known since at least 1850, and quite possibly even earlier. But this doesn't imply that light's speed isn't constant. Identical media will yield identical speeds, and the vacuum of space is pretty much the same everywhere, so light traveling from one end of the universe to the other doesn't change its speed if it doesn't encounter some other medium. Even if light does pass through something that isn't a vacuum, the speed at which the light passes through the medium doesn't persist once it leaves that medium. Once it returns to the vacuum, light continues at the exact same speed that it did prior to encountering resistance. In any case, there's absolutely no evidence to indicate that the speed of light in a vacuum isn't constant.
There's stuff on the internet. Princeton University back 15 years ago speeded light up to 300 times the speed of light. And I covered that in video number 7, I believe, question-answer session. I haven't even seen them in 10 years myself, but it's up, I think it's number 7. They've also slowed light down to, they had it down to 38 miles an hour, and I heard that while I was in prison, some physics laboratories slowed light down to a dead stop. Interesting.
No, Kent, that's not what happened. What Mr. Honvid is referencing is a 2000 paper published by Wang, Kuzmich, and Degariu in Nature, in which it was reported that the group velocity of light had been sped up to superluminal speeds. The group velocity is not what's meant when physicists refer to the speed of light. To understand the bigger picture here, let's take a look at the structure of light. There are 3 principal velocities that can be used to describe an electromagnetic wave: the group velocity, the phase velocity, and the front velocity. This is called an envelope. It tells us what the shape of the wave looks like. The speed with which the shape changes with respect to position is called the group velocity. This is called a phase change. What you're looking at is one wave at two different points in time. The speed with which the peaks and troughs change position is called the phase velocity. The details of these two types of velocity don't concern us here. All that you need to recognize is that these two types of velocities are describing completely different things. Because of this, they can also have completely different values. Here's a wave whose phase velocity, represented by the red dot, is a lot faster than the group velocity, which is represented by the green dots. Notice how between the green dots, you have this recurring pattern of waves. This pattern determines the shape of the wave, and you can see these patterns are slowly moving from left to right. That's the group velocity. Now look at the red dot. It's moving along with the peaks and the troughs, which are moving a lot faster than the overall shape of the wave is. That's the phase velocity. In this particular wave, the group velocity and phase velocity are oriented in the same direction, but they don't have to be. Here's a wave with a positive group velocity and a negative phase velocity. Pay attention to the y-axis. You can see that the peaks and troughs are moving into it, which means that the phase velocity is to the left. The group velocity, however, is very clearly to the right. It is possible for either the group velocity or the phase velocity to be faster than the speed of light. This has been known since at least 1910, and experiments confirming this fact have been performed since the 1980s. The 2000 experiment was just the latest in a long line of tests that showed that the cosmic speed limit doesn't apply to the internal components of light. Because really, the group velocity and phase velocity do not represent the transmission of light from point A to point B. These velocities contribute to the structure of light, not to its propagation. Phase velocity and group velocity do not transmit energy or information. These velocities don't correspond to the transfer of a signal. They can loosely be thought of as internal velocities that define the light structure. So if and when these velocities exceed the speed of light, that doesn't mean that the wave goes from A to B faster than light. A rough analogy for what's happening can be thought of in the following way. A person is on a train that's moving at 40 miles per hour. He pulls out a handgun and fires from the back of the train toward the front, and the bullet travels at 700 miles per hour. Even though there's something inside of the train moving at 700 miles per hour, the train itself is not moving at that speed. In this analogy, the speed of the bullet represents the group and/or phase velocity, and the speed of the train is the analog of the thing that actually represents the light's propagation. The thing that corresponds to the transmission of a signal is the third type of velocity, the front velocity. This is the train's velocity in our analogy, and it's this velocity that never ever deviates from the speed of light. The front velocity is what's referred to when physicists talk about the speed of light. It's this velocity that corresponds to the transfer of energy and information. This is the velocity that we speak of when we talk about the propagation of light from A to B. Unfortunately, the news media didn't recognize this distinction, so they reported that light had been accelerated past the cosmic speed limit, and some even went as far as to report that special relativity had been disproven. To their credit, some media outlets corrected their mistake, but our friend Kent obviously swallowed the story hook, line, and sinker, and 15 years later he's still repeating the same mistake. Don't take my word for it. Here's a statement released by Dr. Wang, the lead author of the study. It has been mistakenly reported that we have observed a light pulse's velocity exceeding c by a factor of 300. This is erroneous. He goes on, our experiment is not at odds with Einstein's special relativity. The experiment can be well explained using existing physics theories that are consistent with relativity. In fact, the experiment was designed based on calculations using existing physics theories. However, our experiment does show that the generally held misconception, nothing can move faster than the speed of light, is wrong. The statement only applies to objects with a rest mass. Light can be viewed as waves and has no mass, therefore it is not limited by its speed inside of a vacuum. Information coding using a light pulse cannot be transmitted faster than c using this effect. Hence, it is still true to say that information carried by a light pulse cannot be transmitted faster than c. So let's recap. Group velocity and phase velocity do not carry energy or information, so even though they can be faster than the speed of light, that doesn't mean that light itself can be transmitted faster than c.
From my understanding, absolutely not. The speed of light is not necessarily a constant, and you cannot tell the age of the universe based on some star that they say is 17.296 billion light years away.
We don't use stars to determine the age of the universe. We use the cosmic microwave background radiation, whose power spectrum we measure using satellites situated in special orbits that allow them to survey the entire sky. This allows us to determine the Hubble constant, which we then use to determine the age of the universe via Hubble's law. Velocity equals Hubble's constant times distance. Dividing both sides by Hubble's constant, and then dividing both sides by velocity, we find that distance divided by velocity is the inverse of the Hubble constant. Well, distance divided by velocity is time, so the age of the universe equals 1 divided by Hubble's constant. The Hubble constant has a value of about 71 kilometers per megaparsec seconds. A megaparsec is 3.0857 times 10 to the 19 kilometers, so converting, we find that the Hubble constant is 2.3 times 10 to the negative 18 inverse seconds. Plugging this into Hubble's law, we find that the universe has been around for 4.3478 times 10 to the 17 seconds, which is equal to about 13.8 billion years. Voila! We've just found the age of the universe. Just for fun, let's see what the value of the Hubble constant would have to be in order for the universe to be 6,000 years old. 6,000 years equals about 1.9 times 10 to the 11 seconds, whose inverse is 5.26 times 10 to the negative 12. Multiplying in 3.0857 times 10 to the 19 kilometers per megaparsec, we find that the creationist Hubble constant is about 160 million compared to the observed value of about 71. I'm just saying.
A, we cannot measure those distances, and I cover that in video number 7, the starlight distances, the parallax trigonometry. How could you possibly know how far away that is? How? It's just not possible. So I cover that video 7.
Well, Kent, parallax is only one of several means by which we can measure an object's distance. While parallax can only be used on relatively nearby objects due to constraints in our ability to resolve more distant objects, other methods allow us to measure objects that are much farther away. For example, if you want to measure intergalactic distances, the distances of the farthest and thus the oldest objects in the universe, the best way to do that is with a standard candle. It works like this. Luminous objects have a quantifiable feature called brightness, of which there are 2 types. Apparent brightness, which is a measure of how bright something appears from Earth, and absolute brightness, which is a measure of how bright something actually is. We can use these 2 types of brightness to determine the distance to any astronomical object. Just put the absolute brightness here and the apparent brightness here, and you'll end up with the distance to the object. A Type 1a supernova, a type of standard candle, has a well-defined absolute brightness, which is why it's called a standard candle. When a Type 1a supernova is at its peak, we know that its absolute brightness has a value of about negative 19.2. It's at this point in time when you want to measure how bright it appears from Earth, at which point you can plug both values into the distance modulus equation and determine how far away it is. Using this method, we found objects billions of light years away, and since they're billions of light years away, it took billions of years for the light from those objects to reach us.
Secondly, we don't know the speed of light's always been consistent.
Kent, there is no evidence that the speed of light in a vacuum has ever changed. So just for fun, let's consider some of the consequences of a universe in which the speed of light changed in such a way as to accommodate the creationist narrative. According to the Big Bang Theory, about 380,000 years after the initial expansion, the universe had expanded and cooled sufficiently to allow electrons to get captured by atoms and thus decrease the density of matter in the universe, which allowed photons to start moving freely without being scattered off of the cloud of electrons that had previously occupied the entire cosmos. The photons scattered off of this huge cloud of electrons one final time before heading off in every direction, including ours, and we can see this last scattering surface today. These photons, according to the theory, have been traveling for about 13.8 billion years. According to Honvid, these photons could not have been traveling for more than 6,000 years, which means that light must have changed its speed in order to give the illusion that the universe is at least 13.8 billion years old because, well, reasons. This would mean that on average, light used to travel 2.3 million times faster than it does today, since Honvid's universe is younger than the real universe by a factor of about 2.3 million. Now what Kent doesn't seem to realize is that in order to change the speed of light, you need to change some other fundamental constants. These are the vacuum permittivity and vacuum permeability constants. The permittivity constant, or the electric constant, can loosely be thought of as a parameter that tells us how easily electric fields move through a vacuum. The permeability constant, or the magnetic constant, can loosely be thought of as a parameter that tells us how easily magnetic fields move through a vacuum. It should make intuitive sense, then, that the speed of light is dependent upon these 2 numbers. Since light is a disturbance passing through electric and magnetic fields, it makes sense that the speed of this disturbance should depend on how easily these fields can move. Using basic algebra, we can see that in our universe, the product of the electric and magnetic constants equals the inverse of the speed of light squared. Now let's imagine a universe where the speed of light is twice as fast. It's easy to see that the product of the electric and magnetic constants changes by a factor of 4 compared to our universe. This might not seem like a huge change, but keep in mind that these are fundamental cosmological constants, and that playing around with them even a little bit could potentially result in a universe that looks very different. So let's consider Hovine's universe, where the speed of light used to be, on average, 2.3 million times as fast as it is today. The product of the electric and magnetic constants is now different by a factor of well over 5 trillion. Well done, Kent. You've just invented a universe that is completely inhospitable to life, and perhaps even completely devoid of structure. The consequences of this equation are catastrophic. It's describing a universe where the electric constant and/or the magnetic constant are ridiculously small. A minuscule magnetic constant will result in a universe where magnetic interactions are all but non-existent. Planets and moons won't have magnetic fields to shield them from incoming solar radiation, making them all inhospitable to life. But things get even worse with a minuscule electric constant. The electrostatic force would become so stupidly strong that nuclear fusion would never be able to take place, since nothing would be able to overcome the Coulomb barrier. This means that there won't be any stars in the universe, so the entire cosmos becomes dark. Not that there'd be much to illuminate in the first place, though. The electric repulsion of protons would be so ridiculously strong that the only atoms in existence would be hydrogen. Welcome to a universe based on creationist physics. And that's not even the half of it. These are Maxwell's equations. They tell us pretty much everything about electromagnetism. Do you notice anything familiar about these equations? That's right, Kent. These guys show up everywhere. These terms, which represent electric and magnetic fields, also depend on the electric and magnetic constants. In changing the speed of light, you are changing literally every equation in electromagnetism. And since electromagnetism is one of the 4 fundamental forces of nature, by changing the speed of light, you are changing 1/4 of all the forces in the universe. In order to even have any hope of making a universe that is both stable and has an average light speed that's millions of times greater than what we have, you need to change all of the other fundamental constants of nature, and in doing so, you're altering the other fundamental forces. In order to make creationism work, you do have to, quite literally, change all of the laws of physics. If you're allowed to change the laws of physics to make the universe 6,000 years old, then anybody is allowed to change the laws of physics to make the universe into whatever they want. So let's wrap this up. Given that there's no evidence that the speed of light has ever changed, and that a change in the speed of light to the extent that you propose would destroy the entire universe, how can we fix the starlight problem? Luckily, Kent has a rational, well-thought-out solution that carefully considers all of the data and calculation. Nah, I'm just kidding. This is what he comes up with.
And thirdly, God's able to make a mature creation. He can make the light and the stars. That's one option.
It looks like an old universe, walks like an old universe, and quacks like an old universe. But since when has reality stood in your way, Kent? When all else fails, throw your hands up and say God did it.